Hello, hi everyone. So now we are in topic 3 for our subject CES513 for the curve fitting method. So in this topic, we will cover about 5 subtopics, which are 3.1 linear regression, 3.2 polynomial regression, 3.3 multiple linear regression, and I will go a bit about general linear least squares, and the last one is nonlinear regression. So for the learning outcomes for this topic, you should be able to analyze, identify, formulate, and solve civil engineering problems using the linear, polynomial, multiple linear regression, and nonlinear analysis. To derive the development of linear polynomial regression analysis equations, fit the given engineering data by suitable regression analysis and compute the strength of the relationship, and predict the future value of the required variable by applying the fitted regression equation. Okay, usually data or any experimental data are often given for discrete values along a continuum. So estimation may require for the points in between these values. This chapter will describe techniques to fit curves to such data so that we can obtain the intermediate estimates. And then some complicated functions are also need to be derived to a more simplified version. All this can be done by applying a curve fitting method. So there are numbers of available curve fitting method, but for now, let us just look for two examples. So the first one is the least squares regression, and the second one is the interpolation. So for the least square regression, where data show a significant degree of error, the strategy is to derive a single curve that represents the general trend. Because some individual data may be incorrect, thus we will make no effort to intersect for each point. Rather, the curve is designed to follow the pattern of the points taken as a group. And then the second one, the interpolation, where these data are known to be very precise. The basic approach is to fit a curve that passes directly through each of the points. Such data usually originate from tables. Okay, before going any further in this topic, I would like to bring you back to the mathematical background of a simple statistic. You may skip this part if you think that you still have a strong memories in simple statistic parameters. Okay, so the first one is the arithmetic mean, which is the most common location of statistic. The arithmetic mean of a sample is defined as the sum of individual data points divided by the number of points. Okay, the second one is the standard deviation, which is the most common measure of spread for a sample about the mean. And then the third one is the total sum of the squares of the residuals between data points and mean. If the individual measurements are spread out widely around the mean, so consequently the standard deviation or SY will be large. But if they are grouped tightly, the standard deviation will be small. Right, the next one is the variance. The spread of a data can also be represented by the square of the standard deviation, which is called variance. So the quantity of n minus 1 here is referred to as the degrees of freedom. Hence, the ST or the total sum of the squares of the residuals are said to be based on the n minus 1 degrees of freedom. Okay, the last one is a final statistic that quantifying the spread of data, which is called coefficients of variation. This statistic is the ratio of the standard deviation, or SY, to the mean. As such, it provides a normalized measure of the spread. Another characteristic that is important in this current discussion is the data distribution. That is the shape which data are spread around the mean. Okay, the data distribution is said to be a normal distribution if it has a symmetric, bell-shaped curve as superimposed in the figure. Alright, the concept of mean, standard deviation, and residual sum of the squares, and also normal distribution all have great relevance to engineering practice. A very simple example is their use to quantify the confidence that can be ascribed to a particular measurement. So a quantity is normally distributed if first is the range defined by arithmetic mean minus standard deviation to arithmetic mean plus standard deviation will encompass approximately 68% of the total measurements. And then the second one, if the range defined by y bar minus 2sy to y bar plus 2sy will encompass approximately 95% of the total measurements. Alright, the figure shown here provides a visual overview of approaches for curve fitting method. It consists of least squares regression, interpolation, and Fourier approximation. For the purpose of our subject, which is CES513, only least square regression will be covered. These regression techniques consist of linear regression, polynomial regression, multiple regression, general linear least squares, and nonlinear regression. Now, we look at the example of least squares regression. The figure shows 7 experimentally derived data points exhibiting significant variability. By visual inspection of this data suggests that a positive relationship between x and y. If a sixth-order interpolating polynomial is fitted to this data, it will pass exactly through all the points. But because of the variability, the curve oscillates widely in the interval between the points. As we can see here, the interpolated values at x equal to 1.5 and x equal to 6.5 appear to be well beyond the range suggested by this data. So there is a more appropriate strategy in approximating function that fits the shape without necessarily matching all the individual points. Okay, from figure C, illustrate how a straight baseline can be used to generally characterize the trend of this data without passing through any particular point. But the sketch is by visual inspection only, and they are imperfect because they are arbitrary. Different analysts would draw different lines. So to remove this subjectivity, some criterion must be established for the basis of the fit. So one way is to derive a curve that minimizes the discrepancy between the data points and the curve. So we will see this in the next slides. There are techniques available for accomplishing the objective stated in the previous slide. One of the example is called least squares regression. It divided to linear least squares regression and nonlinear least square regression. So the first technique is called as linear regression, which fitting the best straight line through a set of uncertain data points. Secondly is the general technique for fitting a best polynomial. Okay, thus you will learn to derive a parabolic, cubic, or higher order polynomial that optimally fits uncertain data. Linear regression is a subset of this more general approach, which is called polynomial regression. The next is multiple regression. It is designed for the case where the dependent variable y is a linear function of two or more independent variables. This approach has special utility for evaluating experimental data where the variable of interest is dependent on a number of different factors. After multiple regression, we illustrate how polynomial and multiple regression are both subsets of a general linear least square. Okay, so the polynomial regression and multiple regression is the subsets for general least squares model. Finally is the nonlinear regression, which designed to compute a least squares fit of a nonlinear equation to data. Okay, now we will start with the main subtopic in this chapter, which is linear regression of the curve fitting method. Alright, the simplest example of a least squares approximation is when we want to fit a straight line to a set of paired observations like x1, y1, x2, y2, x3, y3, and so on until xn, yn. The mathematical expressions for the straight line is y equal to a naught plus a1x plus e, where a naught is the y-intercept and a1 is the slope and the e is the residual, where we can get, when we rearrange the equation, then we can get e equal to y minus a naught minus a1 x. So the residual or the error of this equation is the discrepancy between the true value y and the approximate value. So the approximate value of a naught plus a1x can be predicted by the linear equation. Criteria for a best fit line. One strategy for fitting a best line through the data would be to minimize the sum of the residual errors for all the available data as shown in the first equation. However, this is an inadequate criterion, which depicts the fit of a straight line to 2 points. Obviously, the best fit is the line connecting the points. However, any straight line passing through the midpoint of the connecting line results in a minimum value or equal to 0 because the errors will cancel. Therefore, another logical criterion might be to minimize the sum of the absolute values of the discrepancies, as shown in second figure. It demonstrates why this criterion is also inadequate. For the 4 points shown, any straight line falling within the dashed lines will minimize the sum of the absolute values from the equation. Thus, this criterion also does not yield a unique best fit. The third strategy for fitting a best line is the minimax criterion. The line is chosen that minimizes the maximum distance that an individual point falls from the line. As depicted in the third figure, this strategy is ill-suited for regression because it gives undue influence to an outlier. What is outlier? It's actually a single point with a large error. It should be noted that the minimax principle is sometimes well suited for fitting a simple function to a complicated function. A strategy that overcomes the shortcomings of the approaches is to minimize the sum of the squares of the residuals between the measured y and the y calculated with the linear model. Okay, next is the least square suite of a straight line. To solve a function of y equal to a naught plus a1x, this result can be obtained in conjunction with a naught equal to y bar minus a1x bar and a1. Okay, to determine values for a naught and a1, the sum of squares of the residuals equation is differentiated with respect to each coefficient. So when we differentiate the equations of SR with respect to A naught, the final equation we will get n A naught plus sum of xi A1 equal to sum of yi. While if we differentiate the SR with respect to A1, we will get finally the summation of xi multiplied by A naught plus summation of xi square A1 equal to summation of xi yi. Now we look at the example for linear regression. The question is, fit a straight line to the x and y values in the first two columns of the table given. Okay, for the solution, the following quantities can be computed. First is the number of data, which is n equal to 7. And then the summation of xi multiplied by yi, which is equal to 119.5. And then the summation of xi square equal to 140. Summation of xi equal to 28. And from that we can calculate for the x bar, which is equal to 28 divided by n, 7 equal to 4. And then the summation of yi, which is equal to 24 here. It's already been calculated in the table. Then we can obtain the value for y bar, which is equal to 24 divided by 7, or number of data. Then from there we can calculate for x1 using that equation and obtain 0.8392857. And then we substitute back into the first equation to get a naught, which is equal to y bar minus a1 x bar. Then we will get 0.07142857. Substitute back the parameters value for a naught and a1x. We will get the equation equal to y equal to 0.07142857 plus 0.8392857x. Okay, now we continue with the quantification of error of linear regression. In equation 3.18, shown in the slide, the square of the residue represents the square of the vertical distance between the data and another measure of central tendency, which is the straight line shown in the figure. The analogy can be extended further for cases where A, the spread of the points around the line is a similar magnitude along the entire range of the data, and B, the distribution of these points about the line is normal. If these criteria are met, least square regression will provide the best estimates of A naught and A1. This is called a maximum likelihood principle or in in statistics. In addition, if these criteria are met, a standard deviation for the regression line can be determined. Okay, if the maximum likelihood principle in statistics criteria are met, the standard deviation for the regression line can be determined as SERT SR divided by n minus 2, where S, Y stroke X is called as standard error of the estimate. The subscript notation of Y stroke X designates that the error is for a predicted value of Y corresponding to a particular value of X. Notice that we now divide by n minus 2 because two data derived estimate A0 and A1 were used to compute SR. Thus, we have lost 2 degrees of freedom. Figure shows the regression data showing A, the regression data spread around the mean of the dependent variable, and B is the regression data spread around the best fit line. The original standard deviation SY here quantified the spread around the mean as shown in figure 9a, while the standard error of estimates quantifies the spread of the data around the regression line as shown in figure B. The above concepts can be used to quantify the goodness of our fit. This is particularly useful for comparison of several regressions in the next slide. That is particularly useful for comparison of several regressions as shown in the figure. These are the examples of linear regressions which have small residual errors and large residual errors. To do this, we return to the original data and determine the total sum of the squares ST around the mean for the dependent variable. So in our case is Y. This is the magnitude of the residual error associated with the dependent variable prior to regression. After performing the regression, we can compute SR, which is the sum of the squares of the residuals around the regression line. This characterizes the residual error that remains after the regression. It is therefore sometimes called as an explained sum of the squares. The difference between the two quantities, ST and SR, quantifies the improvement or error reduction due to describing the data in terms of a straight line, rather than as an average value. Because the magnitude of this quantity is scale dependent, the difference is normalized to ST, where R square is called as coefficient of determination, and R is called as correlation coefficient. For a perfect fit, SR equal to 0 and R equal to R square equal to 1. This signifies that the line explains 100% of the variability of the data. For R equal to R square equal to 0 and SR equal to ST, D shows that the fit represents no improvement. Now we look at example for estimation of errors for the linear least squares fit. The question is compute the total standard deviation, the standard error of the estimate, and the correlation coefficient for the data in example 3. So for the solution, First of all, we need to calculate the standard deviation, which can be obtained from the equation of Sy equal to ZST divided by n minus 1. And then the second, we calculate the standard error of the estimates by using equation Sy stroke x divided by ZSR over n minus 2. Thus, because Sy stroke x lesser than Sy, the linear regression model has merit. The extent of the improvement is quantified by the standard error of estimate and the correlation coefficients of R square or R. So this result indicates that 86.8% of the original uncertainty has been explained by the linear model. Next, test your understanding by doing the exercise 1. The question is, use least squares regression to fit a straight line to these data. So A, along with the slope and the intercept, compute the standard error of the estimate and the correlation coefficient. Plot the data and regression line. B, if someone made an additional measurement of x equal to 10 and y equal to 10, would you suspect, based on a visual assessment and the standard error, that the measurement was valid for faulty? Justify your conclusion. The next subtopic is 3.1.4, Linearization of nonlinear relationship. The first step in any regression analysis to plot and visually inspect the data to ascertain whether a linear model applies. So if we can see the left figures, it shows some data that is obviously curvilinear. In some cases, techniques such as polynomial regression, which also be discussed in the chapter, are appropriate. For others, transformations can be used to express the data in a form that is compatible with linear regression. The exponential model, where alpha 1 and beta 1 are constant, as depicted in figure A, the equation represents a nonlinear relation between y and x. Another example of a nonlinear model is a simple power equation, where alpha 2 and beta 2 are constant coefficients. This model has wide applicability in all fields of engineering. As depicted in figure B, the equation is nonlinear. The third one is the saturation growth rate equation, where alpha 2 and beta 2 are constant coefficients. This model represents a nonlinear relationship between y and x, as in figure C, that levels off as x increases. Nonlinear regression techniques are available to fit these equations to experimental data directly. However, a simpler alternative is to use mathematical manipulations to transform these equations into a linear form. Then, simple linear regression can be employed to fit the equations to data. For example, exponential equation can be linearized by taking its natural logarithm to yield ln y equal to ln alpha 1 plus beta 1 x. A plot of ln y versus x will yield a straight line with a slope of beta 1 and intercept of ln alpha 1, as in figure D. Equation B is linearized by taking its base 10 logarithm to give equation E. Thus, a plot of log y versus log x will yield a straight line with a slope of beta 2 and intercept of log alpha 2, as in figure E. Equation C is linearized by inverting into equation F, Thus, a plot of 1 over y versus 1 over x will be linear with a slope of beta 3 over alpha 3 and an intercept of 1 divided by alpha 3 as in figure F. So now we look at example 5 for the linearization of a power equation. So the question is, fit the simple power equation to the data in table below using a logarithmic transformation of the data. So the table is given in the picture, and for the solution, from the simple power equations of y equal to alpha 1 epsilon beta 1x, figure A and B here is a plot of the original data and the plot of transformed data respectively. A linear regression of the log transformed data yields the result of log y equal to 1.75 log x minus 0.3. From there, we can obtain the intercept y is equal to log alpha 2 equal to negative 0.3. Using the anti-logarithm, we can obtain alpha 2 equal to 0.5 and the slope is beta 2 equal to 1.75. Thus, the power equation is y equal to 0.5x power of 1.75. This curve, as plotted in figure A, indicates a good fit. Before ending the subtopic 3.1, please do the exercise 2 for linearization of nonlinear equations. The question is, an investigator has reported the data tabulated here. So it is known that such data can be modeled by the following equation, which is x equal to e power of y minus b divided by a, where a and b are parameters. So the question A, use a transformation to linearize this equation and then employ linear regression to determine a and b, based on your analysis, predict y at x equal to 2.6. Okay, good luck.